So, hi everyone. Uh, Welcome to the eighth week of this tutorial session. In this week, we will solve some questions regarding this Maxwell equation in linear and dielectric media, and then we will derive how we can derive a refractive index of a medium from Maxwell equation. At least how we can relate the refractive index in a medium with Maxwell equation. So I will wait for few more minutes, then I uh, so that people can join, then I will start. Okay. So I will wait uh, around 2 or 3 more minutes so that others can join, then I will start.
Okay, sir.
Okay, I will wait for 1 more minute. At 17:05 we can start. In the meantime, so as you guys know that I will be recording this session, and I will upload this video on YouTube where you can watch this later on based on your convenience. The video and the PPT used in this session will be shared with you. So the video link will be shared and the PPT link also will be shared with you. So you can access them later on and you can watch and you can ask any doubt on the forum also. So now, uh, in previous week we have learned about the Maxwell equation and how we can derive the electromagnetic wave from this equation. Now, in this today's session, we will learn about Maxwell equation in linear and dielectric media. So, why this is linear and how this supposed to be, like what does it mean by linear? I will explain later on, and how we can relate the refractive index in a medium with the uh, with with Maxwell equation. Okay, so let's start. So as we know that Maxwell equation is given in this form. So where del dot E is equal to 1 over rho, 1 over epsilon naught into rho. This is nothing but a Gauss law. So rho is just charge density present, and this is equal to the divergence of electric field. And second is the del dot B is equal to 0. This is related to the divergence of uh, magnetic field, which is 0. And then the third law is related to the del cross E equal to minus del B over del T. It is related to the Faraday's law, where any change in the magnetic flux gives rise to an electric potential uh, across a medium, like where the flux is changing. So the the derivative form of that equation, I mean the Faraday's law, is given by this del cross E is equal to minus del B over del T. And the last equation, which is del cross B is equal to mu 0 J plus mu 0 epsilon 0 del E over del T. So you know that in the last tutorial session, we get to know like how this del E over del T term is included in the fourth equation. So it's it's the it's the term that Maxwell introduced in the previously well-established formulas. So, and after the inclusion of this term, we can see that the divergence of this del cross B goes to 0, because divergence of any curl quantity should be 0. Then the right hand side is del dot J is equal to del dot E over and the partial derivative of del dot E over del T. So that means this is nothing but the rho divided by time, and this is the divergence of J, and this gives us equal to 0 is a continuity equation. So it's indeed now the inclusion of this del E over del T terms gives us the complete electromagnetic equation, complete four electromagnetic equations. So, and using that we have derived uh, electromagnetic wave equation in a medium. Now, today we will see how this Maxwell's equation gets modified in a linear dielectric media. So, what do I mean by linear? And so, let me explain. So, first, there is this Maxwell equation in a medium, where you can see there is the introduction of the displacement vector that comes in place of this electric field vector. So del dot E is equal to rho F, where rho F is the free charge density, and here rho was the total charge density. Okay, so now the first equation is modified, where you have to only take care of the free charge densities, and you have to you just forget about whatever is there after applying this electric field or any field. So because there can be some bound charge, etc. There can be induced charge inside the medium or on the boundary. So there's a sigma bound on the surface, and the sigma and the rho b inside the material itself after the application of field. So deriving the del dot E will be like much complicated, but if you consider only the del dot D quantity, you just have to equate it uh, up with the free charge density. And the free charge density, you know that you have applied. So you can easily calculate the del dot B, and hence you can calculate the del dot E. And how you can do that, I will let you know in the coming slides. And the next equation remains as it is because the divergence of magnetic field is zero because it's a solenoidal kind of field where there is no source and there is no uh, uh, sink. It's like this is continuously emerging and going back where it uh, emerges from. And then the next one is remain at it is del cross E is equal to minus del V over del T. But the next one you can see this is del cross H is equal to JF plus del D over del T. So you can see that JF earlier it was the total current density is now modified to the free current density, and that is there is another term which was del E over del T is has been modified to del D over del T in a media. Now our first question is write the Maxwell equation in a source-free medium. Okay, so let's now before writing this, we need to understand what do I mean by linearly dielectric media. So let me share my screen and 1 second. I will share my screen and then we can see what does it mean to have a linearly dielectric media. Okay, guys, wait a minute. I just need to change some things. So first, I need to change the background. This look, okay, this, the background color like this one. So now we are good to go. So I will share my screen now with you guys. So what does it mean to have a linearly dielectric uh, medium? Is that once the okay, okay, you have you have you have a media where you apply some electric field or magnetic field, then what you see is this effect of this electric field is uh, linearly proportional to this. It means okay. So because we know that d vector is equal to nothing but epsilon 0 e plus d vector. Okay, but this thing epsilon 0 e plus 1. Okay, this is d vector. This we know. This is the displacement rule. So epsilon 0 e plus t can be written as because p is proportional to the directly proportional to the applied electric field with a susceptibility. So this is electric susceptibility, and then you can write it like this. So the displacement vector is written as the epsilon 0 1 plus chi e and e. So you can write this as epsilon 0 epsilon r e vector t vector, something like that. So you can see that here I have used something, and this is related to P is now linearly proportional to E, and the proportionality constant is given as chi. So, so this is saying this equation is saying that the induced charges are linearly proportional to applied electric field. Okay, that means whatever field you are applying, there is some charges that are being induced in the medium, and the charges are such that it is linearly proportional to the field strength that you have applied. And this linearity is is saying that it's a linear media. Means if let's suppose if it were like the induced charges were like this, where it was something around like this. So where this is chi 2 and this is E2. So here you see that the induced polarized charges are proportional to the square of the electric field. So what where this is true is not a linear dielectric media. Okay, so you have to keep in mind that where this relation is true, this is a linear dielectric media, and with the help of this, we have displacement is equal to epsilon naught epsilon r. You can say relative some quantity in E. So this is how you can write it. And if you write the equation del dot E is equal to uh, rho upon epsilon naught and the medium constant epsilon r, so you can easily see that epsilon naught epsilon r del dot E is nothing but rho f free charge, and this is given as del dot t is equal to rho f. So we can see that the first equation is del dot t is equal to rho f. Okay, so this can derive this, and then now the second equation is nothing but it remains the same, that del dot p is 0. The third equation, similar to the electric field, you can similarly write b that is proportional to the, because we have this equation, we have this Maxwell equation del dot E is equal to del B over del T. So you can, sorry, okay, where is this? Okay, here. So del dot B is equal to 0, and then del dot B equal to 0, and then there is this del cross E is equal to del B over del T with a negative sign. Then the fourth one gets modified because you have now B is equal to mu 0 or mu h. Okay, B is equal to mu h, and in the vacuum it was like B is equal to mu 0 h. So in the media it's mu h. Now you can write this del, we remember this del cross B is equal to mu 0 epsilon, so mu r in the media, right? So it's a mu j and mu epsilon del E over del T. Okay, so but we know that S B is equal to mu proportional to h. From here we can write this like this, and then J, and then free, it's the free charge current density mu epsilon del E over del T. Okay, so we can write this as del cross H is equal to mu j. Okay, mu is gone from both sides. Mu j. Okay, so this will be jf plus this mu is gone, then it remains like epsilon e this del e over del t, and then this gives rise to del cross h equal to jf plus this is nothing but the displacement vector del d over del t. Now what I'm trying to say, oh, okay, so you can write this whole thing as some epsilon e, because epsilon naught is just some relative constant, it's a permeability in the vacuum, but this total thing you can write as epsilon. So it's like this. So the fourth equation becomes this. So this is the linear. These are the four equations in a linear media. So where we know how they are arriving, because this electric field electric field is inducing a polarization. Okay, so this electric field is inducing a polarization that is proportional to this its magnitude, and this proportionality we can see it's linearly dependent on the magnitude. So this is how it is, and then again there is this magnetic field which also induces a linear magnetization in the media, magnetization moments in the media. So this is also linearly proportional. So these both lead to the linearly dielectric media. And uh, in linearly dielectric media, the magnetization is usually mu r is equal to assumed to it is assumed is equal to 1, means the material is not magnetized. So this is how the equations work. Now, now the second question is this. Okay, what is this? The second question is write the Maxwell equation for linear dielectrics. Okay, so first one is the source-free media. Now, what I have to explain what is a source-free media. So we can write the equation again. It's a del dot E del dot D is equal to JF, sorry, rho F. It's a current. It's sorry, it's a charge density, and that's it free. Means it's the charge you have put in the media. And then del dot B is 0, and then third is del dot del cross E is equal to minus del B over del T. The fourth one is del cross H is equal to J F free plus. Okay. Now, what do I mean by source free? So source free means that free charges are 0 in the media, and the charge current is also 0 in the media. So that means the Maxwell equation will be reduced to this 0. Second is del dot B equal to 0, and third one is del cross E is equal to minus del B over del T, and the fourth one is del cross H is equal to J free plus del D over del T. Okay, so now because it's source free, I have written GLF 0, so we have to directly equate these two, and this is how you can get a source free Maxwell equation in a media. And also I explained the second question also, that what are write the on the Maxwell equation for linear dielectrics. So this is how you can write down the Maxwell equation for linear dielectrics. Now our next question is a wave equation in a linear dielectric media. Okay, so let's see how we can write a wave equation in a linear dielectric media. So we know that let's go back to Maxwell's equation that in source free media, so it's a del cross E and it's zero. So you can write it like this because source free. The second one is del dot B, always zero. So you can write it like this. The third one is del cross E is equal to minus del B over del T. And the fourth one is del cross B is equal to mu zero. Sorry, so mu r because it's a linear dielectric media, so you can write it as a mu j and mu epsilon del E over del T. Now what you can do, as we have done earlier, we have to just do the uh, do the second. You have to take the curl of third equation. So curl of this third equation will be uh, something like del of curl of E and have minus del curl of B on T. So you can write this down as del dot E. Sorry, it's not dot. And you can write it like this del square E using curl identities of a vector. And this can be minus del cross B. But let's leave it for a moment like this. And you can see something here that is also there in this equation. So this is what we are after. So but del dot E is 0 in the source free media, so if this goes to 0, you can write this as del cross E and minus del over del T. Now put this equation 4 here because you can see there is del cross we already present. So mu j plus mu epsilon del E over del T. Now what you can do, can just take the time derivative inside this bracket and you have this del t. But again, because we are talking about the source free, so j also should be as 0. So let's put this term to 0. So it goes to 0 here also. So only the thing that is there inside the bracket is just del e over del t. So you can write as minus del square e is equal to minus mu epsilon del square E over del t square. And we can see that this minus sign goes away from both sides. Now, if you compare this with the wave equation in a vacuum, so you have this mu 0 epsilon 0 del square E over del t square, where we know that mu 0, this where v is where the light was light velocity c square. Okay, let's write it down like this. So if you write mu 0 epsilon 0 in the denominator, then this is the velocity, right? Because okay, so because this is the permeability in the medium and the permittivity. So uh, this multiplication and the inverse of that gives us the light speed of light c is speed of light in a vacuum. But in a media, the equation we have is del square E is equal to mu epsilon del square E over del T square. Now what we have is we can write this as mu. Okay, so if you define something like this, mu r is equal to mu over mu 0 and then epsilon is equal to epsilon r over epsilon 0, then you can write this r epsilon r, sorry, and then mu 0 epsilon 0. and you have this del square E and del square E over del T square. So we can easily identify this is 1 over C square del square E over del T square, and this is the del square E. And what is this? This is this is the okay. So this is some quantity. Let's say it's some K, not K. Let's say it's A. So we can see if we have, and we know that in the medium refractive index is defined as n is equal to C by V. So that means if we compare it this thing like this, so you can see we have the velocity upon A. So velocity upon A. So this would be some velocity, right? Let's say it's A square, the constant is A square, so C by A, something like this. So it should be velocity square. That means, okay, so in the medium, the equation modifies to this 1 over V square del square E over del T square. Okay, and let's compare it with the equation that was in the vacuum. The vacuum equation was like 1 over mu 1 over C square del square E over del T square. So that means the velocity has reduced from from C to V by a factor of A. So this A is nothing but this is called this A. This A is called refractive index of a medium. So where it's called N, and it's equal to here in our case A, and this is nothing but mu r epsilon r. And for a non-magnetic linear media, this N h under root of epsilon r, and epsilon r, this epsilon r is called, because mu r is 1 for this non-magnetic media, so it's like this. Epsilon is called the dielectric constant of a media. So it means that n is under root of a dielectric constant of media. So we can see from this equation that the dielectric this refractive index concept comes from this Maxwell equation in a linear dielectric media, and it is and its velocity means the electromagnetic waves velocity gets reduced by a factor of n, and this is what are called refractive index of a media. So it's a ratio of the light speed in vacuum upon the light speed in the media. Okay, and this is proportional to the under root epsilon r, the relative dielectric constant. Okay, so let's go to our next question. Next question is, what is the refractive index of a media? So we have just seen that this is the refractive index of a media. Now, so this is the refractive index of a media. This is how we have seen. because first we derived the Maxwell equation all the way. Maxwell e- Max First we had this wave equation from Maxwell equation in a media. Then we derived the how this modified Maxwell's equation in a linear media gives rise to a reduced velocity of the electromagnetic wave, and how it is related to the dielectric constant, and hence the refractive index. So we have defined the refractive index in a media, how you can define it. And for non-magnetic media where mu r is less than 1, we have this n is equal to under root epsilon r. So it's directly proportional to the square root of a dielectric constant. Okay, so let's go to our next question. The next question is, let E be this, where E is the sine wave, plane wave, and the V is this magnetic component is also a plane wave. Then they are asking that show us that this velocity is under root mu over epsilon. Okay, so we know the Maxwell wave equation, that del square E is mu epsilon del square E over del T square. So in the one dimensional where this is propagating in a plus x direction, so it's propagating in plus x direction. This plane wave is propagating plus x direction. That means we can this is this del square. Del square in 1D will be del square over del x square. So let's and we know that E is given as E equal to some constant E naught sine kx minus omega t plus phi. So some constant E naught sine kx minus omega t plus phi. And if we take the double derivative of this del E, first let's take the single derivative. So we have E naught sine goes as cos kx minus omega t plus phi, and you have the k here. Then again you take the double derivative of this. So you have this E naught cos goes as minus sine kx minus omega t plus phi k square. Now, if you take the double derivative, this time derivative of this electric field, as the right hand side would be double derivative. So we are going to calculate that, and we have okay del square. Okay, so will be like E naught. Okay, so E naught and sine. It will be cos kx minus omega t plus phi into minus omega, and then del square E del t square will be E naught sine kx minus omega t plus phi, and this will be minus cos, and this is also like this. This will be omega square, but minus will be here. Okay. Now once you put all this, so you have E naught will cancel out from both sides. You will have omega square is equal to k square, and mu, mu epsilon. But this mu epsilon will be k square over omega square. And if we know that this is nothing but 2 pi by lambda into 2 pi by 2 pi by t. So this is like this, and the square of that. So 2 pi will cancel out. It's nothing but t by lambda square mu epsilon. But we know that this is nothing but 1 over v square in epsilon. So from here it will be v is equal to under root mu over epsilon. So this is how we proved it by putting this equation back into the Maxwell's equation. Now, uh, this is related to the, again, we can say this velocity is related to the permeability and permittivity of that media. So that they affect the electromagnetic waves velocity, and they affect in a such a way they reduced its velocity. Now our next question is, okay, before going to that, first we have to recall that what is a Poynting vector. The Poynting vector actually describes the flow of energy in a media, and it's along the direction of propagation. So if you have a source where you know the electric field and the magnetic field direction, you can calculate the Poynting vector by just doing the cross product between the electric field and the magnetic field. Okay, so you can calculate from there. Now, what how this Poynting vectors gets modified in a media? So that is our that is next thing. So we know that the magnetic field is proportional to the applied field and intensity. So from there you can you can calculate you can calculate the you can calculate the B, and this is how this Poynting vector is being rephrased in a dielectric medium. So this mu zero, if you notice from here, this mu zero is now changed to mu because of this new dielectric constant. Sorry, new permeability of this media, and we know that the relation in this media is given by this magnetic field is equal to mu into the magnetic field intensity. So we can see the in linear dielectric media, this S vector is equal to E cross H over mu into mu. So mu cancels out and you have this only E cross H. So our next question is, write down the energy density in a media for plane waves and its relation with the Poynting vector. Okay, so we have to write down the energy in a media, and then we have to write the relation with Poynting vector. So okay, so let's start from here. That we know that in a media, the energy density is given as u. Uh, that's the average of 1 by 2 the electric field and the displacement field, and similarly 1 by 2 this magnetic field and the intensity in the medium. So we know that this is nothing but 1 by 2, and because this electric field is linearly proportional, sorry, this displacement field is linearly proportional to the E. So we can write this as a epsilon E, and similarly, sorry, let me write it epsilon E, and then average, and then 1 by 2 or this average also. So it will be 1 by 2. You can take it out because it's a constant. It's a B. But we know that B is proportional to the mu H in the media. And similarly, this D is proportional to the epsilon E, right? So you can write this like this. Okay. But with uh, division with mu. Now you have this 1 by 2. Epsilon is a constant, so you can take it out. Epsilon e 1 by 2 mu b square. This is the average of this. But we are given a plane wave solution. Plane wave solution for the electric field or the electric field and the magnetic field. So we have the average. Okay, so the electric field is nothing but some constant into sine kx minus omega t plus phi, something like this. And the magnetic field is some constant v0 sine kx minus omega t plus phi. Okay, so we can clearly see when we do this E dot E, it's nothing but E naught square sine square kx minus omega t plus phi. But we can see that this is a periodic function, and if we take the average on the both sides, E naught square sine square E naught is a constant, it will be out of sight. So the average plus phi, and this can be written as 1 by 2 because the average of this cosine square is 1 by 2 inside a periodic thing. So that means this what we are doing here is nothing but, okay, let me write what do I mean that by the average of this phi, and the average is nothing but, okay, so we are taking the time average here. So let's say at x is equal to 0, we have this, and let's say the phi is also 0 for our convenience, so it's nothing but sine square omega t, and then we are taking the time average and then dividing with the time and integrating between 0 to t. But we know that t is 2 pi by omega, so omega over 2 pi, and here it goes from 2 pi by omega, so sine square omega t into dt. Now we know that sine square omega t is nothing but uh, cos 2 omega t minus 1, because, okay, this is plus 1, this is minus and over 2. It's a cos, because we know that cos 2 theta is equal to 1 minus 2 sine square theta by, okay. So sine square theta will be always 1 minus cos 2 theta over 2. So this is how it is. Now, if you calculate the average of this, means this is A, so this A will be omega over 2 pi 0 to 2 pi by omega into uh, what you can say is this 1 minus cos 2 theta is 2 omega t over 2 into dt. But uh, this integral comes out to be dt by 2 minus pi cos 2 omega t into dt. Let's close this. So first one is omega over 2 pi into this 1, so t by 2 into 0 to 2 pi. And this is a periodic function. So it can be, this is cos omega t, integral is sine omega t, sine 2 omega t upon 2 omega t, 2 omega, sorry. And then you have to just put the limit. And then this is nothing but simplified form of this is t by 2. So t is 2 pi by omega. So put it there, 2 pi by omega upon 2 is there. So 2 is here also. But sine 2 pi by omega it's like sine 2 into 2 pi, and omega is cancelled out omega and upon 2 omega. That does not matter because and minus sine 0. So sine 0 over 2 omega. So it's like 0, and this is also sine 4 pi 0. So it will be 0, but what you are left with is omega over 2 pi into 2 pi by 2 omega. So it comes out to be 1 by half, and that means whatever integral you are calculating here, this energy density, because these functions are calculated here. So this is okay. So this is also e square, right? So you can see the proportionality is to sine square with the amplitude out. So, and we got the average is 1 by 2. So let me write that again. So what you are doing is 1 by 2 epsilon under root e vector square plus 1 by 2 mu b vector square. Now this e vector square was proportional to the e naught square, but sine square of kx minus omega t plus phi. And when we are taking the average, we are taking the whole average, and this e naught square is constant, so it comes out naturally, and sine square kx minus omega t plus phi remains inside, and this is nothing but we have just calculated, it's just 2 is naught square by 2. And similarly, we can write for b square, so it will be b naught square, and the sine square of kx minus omega t plus phi. So it will be b naught square by 2 also. So the energy that we are calculating will be half epsilon E naught square plus half epsilon, uh, sorry, half V square, V naught square. Okay, so it's already half, and half. Okay, so this is what it will be. Now we know that uh, it will be. Let me simplify this. Okay, oh, okay, we are missing something. Okay, now what we know that for a plane wave, for a plane wave, we have del cross E is equal to minus of del B del T. That means there is relation between this electric field and the magnetic field. So if you have this wave that is going in x direction and you want to calculate the curl of it, so uh, the only non-zero component that you are going to get is for plane wave actually, sorry, for plane wave we can write, for plane wave we can write this v naught is equal to v naught, the velocity, and that is nothing but under root of mu epsilon, because v is proportional to, just we have derived just v is proportional to under root of mu epsilon. So this is how it is called. Now, so energy density 4 epsilon naught, sorry, epsilon e square, naught square plus 1 by 4. And if at the place of b naught, we can write mu square, sorry, mu epsilon e naught square upon mu. And this is nothing but 1 by 4 epsilon e naught square. We cancels out with this epsilon e naught square, and this is nothing but mu is equal to 1 by 4 to 2 epsilon e naught square, and this comes out to be by 2 epsilon e naught square. So if you can recall, the energy density of electromagnetic wave in the vacuum. Watch, recall, view, vacuum was 1 by 2 epsilon naught E naught. So you can see there is this change. Uh, okay, now you can now the pointing vector, now the magnitude. So in medium, in the now the pointing vector magnitude for the pointing vector magnitude, the medium is given as S magnitude is equal to E cross B, right? So you can write this as uh, E over mu. So it will be like EB over mu, but we already know that EB is related with the B, and this is the average of this. So we can write the average. Okay, and this B is equal to E is equal to P. Magnitude of P is equal to this and this. So we can write it here like and okay. So this is this and this energy. This is the pointing vector. So we can write this with the velocity. Okay. How we can get from here to here is through using this. So we can get the velocity and the epsilon naught E square. But let me derive this for you. So what you do, you put E and then E and the value of V to E is equal to V cross V. So you put V and then this. Okay, so what we have? We have two things. V is equal to also uh, so X. We have used it earlier, right? So we have used this again. So we can write it like this. So V on E and mu. Sorry for the disturbance. So it's that's E square, okay, upon V to V, and V is nothing but uh, 1 over under root mu upon epsilon. So we can write this as so we can write this as E square epsilon over mu, and this is half of that because the half E naught square of E naught square. Now you can write it multiplied with this will be you can you can multiply both sides with under root epsilon. So you can write this like epsilon and here this epsilon is there. So this comes this and this becomes this. So it becomes by 2 epsilon naught square square into epsilon, and this is nothing but the velocity. So this is how you can change it. So we have this s vector like this. The amplitude of s is nothing but of epsilon naught of epsilon e naught square to the velocity. So you can write it like the energy density, this into the velocity multiplied with the velocity in the media. So this is the amplitude. And this is the magnitude of this Poynting vector. And this is given by this. Okay. Now, what is the next question? Okay, so we have derived the energy density in a medium for plane waves and a relation with the Poynting vector. So we recall that we have used this this thing here, and it's true for plane wave. So that's why we can write this like this. Now, the next question is the magnetic uh, the magnitude of Poynting vector. Sorry, this is a typo. The magnitude of a Poynting vector and electric field vector are respectively S and E. Then which of the following is true? So as we can see from our previous derivation, that the amplitude, if you ignore the half factor, so it's proportional kind of E square, and then it's in a vacuum. So you can see from the very first equation, like from here, this magnitude. So from this magnitude it was like under root of epsilon and mu up into E square. But in vacuum, epsilon is epsilon r, epsilon naught, and mu is mu r, mu naught. But in vacuum, for vacuum condition, what happens? Mu becomes 1 and epsilon r becomes 1. So with this epsilon becomes epsilon naught and mu r becomes mu naught. Sorry, this total mu becomes mu naught. So it's true for a vacuum case. So we have this magnitude is nothing but epsilon naught over mu naught into E square. Okay, this is how it is. Now you can easily see that the first is true, but if you and others are not true because the ratio is of epsilon naught over mu naught. Okay. Now, okay, so others why others are not true because you can see that for the second option, because okay, so this is what I have written because we have seen that this S is equal to from here from this very first because this was the energy density. This is the relation between the Poynting vector and the electric field and the magnetic field in a medium. So that's why because S is equal to the 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 S vector was S is equal to the definition was this E cross B, right? And in the vacuum it was like 1 over mu 0 E cross B. Okay, so this is gives this means the once you calculate the magnitude, so it's magnitude of this, then the magnitude of E and B. Okay, so this gives rise to this. This is how it is done. And once we did this, then we have found that this is the relation. So we can calculate the S here, magnitude of S like this. And we know that there is a relation between magnetic field and the electric field that was given as V and the magnitude of V like this. So we put that here. So we replace that V with E by V, and then what we found that V already we have seen was proportional to under root mu or of epsilon. So we put this V here because you can see this equation here, and from here did we kept this E square as it is, we kept this mu as it is, uh, and epsilon goes on the top, and from here you can see clearly that why this is like this, means the proportionality between this S and E vector. So, and the you can see this epsilon is on the top and the mu is on the bottom. So after this thing, we can write this, multiply this with epsilon, and then this top and bottom. So both, so this is how this epsilon comes here and here, and it was already there. So it's epsilon, and epsilon means nothing, the velocity again reverse. We put it back, so it becomes epsilon into V, and now simplified it's like this. But we know that this is the energy density, and then this is V, so the velocity. So it's a multiply of the energy density into the velocity magnitude. Now this is the Poynting vector. So Poynting vector in a vacuum is proportional to this. Ignore the half factor for now. The, the matter. Okay. So this is how it's coming out to be. Now our next question is, and others, some are not dimensionally correct because s square it's had to be e to the power 4 somehow because the definition says e into v and v is some velocity into v. So again, if you are doing s square, it has to be kind of e square into b square or e to the power 4, something like that. It cannot be directly proportional to e or separately proportional to e. No, it has to be the twice of the, means it has to be either e into b or e square or b square. The, if you square it again, so it has to be of order of 4. And again, this was the reverse. This was also not the true. So we have found that the first answer, this S is equal to E square, epsilon naught over mu naught is correct. Okay, let's go to our next question. So next question is, for a plane wave of angular frequency omega, propagation vector k in a media, Maxwell's equation reduces to this. So which it can reduce. So we can see. So we can see that a plane wave can be written like E vector is equal to E naught vector sine A r minus omega t. Okay, so this is a plane wave. Now what it is saying that there is this B vector also, E naught sine of k dot r minus omega t. Okay, now what is being said that somehow we have to, with this cage, right? Cage, it denotes the direction of propagation. Then somehow we have to relate this uh, k vector with the derivative. So let's say we check it for this del dot e. So del dot e will be like I into del over del x e x plus j into del over del y, ey plus k into del over del z, ez. Okay, but if we are thinking in terms of a spherical coordinate, so the divergence can be taken as like E naught a constant, it will come out. So, so the only thing that will be here is sine k dot r minus omega t. Okay. So recall a formula. If you have divergence of a function multiplied with a vector, so you can write this as del dot f to a plus del dot a to f. Okay. So if this is a formula, so you can see this is the vector and this is the f, and this is the vector a. So if E naught has some component in ex E naught x, ex E naught x plus E naught y, and then y cap E naught j, z cap, then the divergence del dot E, that will be, first you have to take the divergence of this and multiply the vector. So E naught vector multiplied with this divergence of f. Okay, so not del dot f, means you have to take the gradient of it. Sorry, it's gradient of f multiplied with dot product. So you have to take the gradient like this, and then again the dot product of this into the f. So dot product of this will be like del over del x E naught into uh, plus del over del y E naught y plus del over del z E naught z. So you have this f is nothing but sine kr minus omega t, and here it's E naught into the del of f, and the del of f is given as I del over del x f j del over del y f plus k del over del z f. So that means here we have to calculate this. So it del f. So del f will be I del over del x sine kx minus plus ky kxx ky y plus kz z. This is k dot r minus omega t. And similarly for j del over del y sine kxx plus ky y plus kz z minus omega t. And again we have this z component del over del z sine of k z z, sorry, sine of kxx plus ky y plus kz z minus omega t. And now when we do this derivative, we have this I, and del over del x is nothing but kx cos uh, kxx plus ky y plus kz z minus omega t. And again, similarly for others, it will be ky j cap cos kxx plus ky y plus kz z minus omega t. And for k kz cos kx plus x ky y plus kz z minus omega t. Now, if all this is here, you can write it like this. And the other terms, if you consider that, these are uh, zero, means that this is constant, the amplitudes are constant. So for a plane wave, it's the case, usually it's zero. So the second terms goes to zero. What we have is del dot E. Del dot E is equal to, okay, del dot E will be uh, zero. Okay, so for a free thing, it's zero. So you have now also you have to take the, okay, so del dot E is del of F to E naught plus del of E naught into F, but this is constant, so it's zero. It remains this, and we have calculated here, and we have to just multiply it with the component. So kx ex into cos kx plus x ky y plus, okay, let's write it down at k dot r again minus omega t, and it's same for all others, so it can be taken out as a common thing. So I kxx plus j ky ey, sorry, it's ex naught ey naught plus k kz kz e z naught into cos of k dot r minus omega t. Okay, so from here we can write this as k vector. If I if okay, so there won't be any vector now because I j k, it's a dot product, so it will be here. So it can be written as k dot e into cos of this k dot r minus omega t. Okay, so del dot E will be something like this and equal to zero. So this is obviously non-zero for some constant phase. So that means k for some arbitrary phase, it will not be zero. So k dot E is zero. And similarly, we can prove that del dot P is equal to zero. This suggests that k dot P is zero. And third, it will be like del cross B is equal to del cross E is equal to minus del P over del T. So we can also calculate that this will be k cross E into the del B over del T, the cos phi, and the cos phi will come out something like this. So omega will be here, and minus minus will be plus, and it will be like del B over, okay. So both sides will cancel out. So it will be like B naught, uh, K E naught, and B naught, and this will be K by omega. Okay. So now the next thing is we have to also prove that, okay, we have to also prove this the, for the other one. So for the other one, it will be like the fourth one. It is del cross B. It's a source free term. So we have to just calculate the mu epsilon del E over del T, and del E over del T will give you omega, and the sum uh, uh, there will be a minus sign because of this derivative, and they both will cancel out, and this del cross B will be something like, sorry, let me write this down. So this is del cross B is equal to the source free term is mu epsilon del E over del T. But what I'm saying that if you calculate the del cross B, it will come out something like K cross P naught. Okay, and some cost term, cos kx minus k dot r minus omega t plus phi, and the del E over del T here will be something uh, mu epsilon minus omega cos k dot r minus omega t plus phi. I phi is there. So now if you equate both sides, so you have not, it will be not mu epsilon, it's this, but if you equate both sides, it will be k cross p naught, k cross p, and omega, this is minus and mu epsilon, and then you have this cos equal, so they will cancel out this. Now we have this, we have proved this. So the third and fourth, now we know p h equal to mu h. So everywhere where p, you replace it with mu. So k cross mu h is equal to minus omega mu epsilon. Mu cancels out here, so k cross h is equal to minus omega epsilon. There should be this, it's the k cross p naught, right? So p naught will be also there, a vector. So here it's like this, vector, not vector. You So this is how it reach. It's omega. This one is now here, and the other one, the del cross E is equal to minus del B over del T. So it comes out to be del K cross E is equal to minus omega B naught, omega and B. So you can replace it to mu omega into mu B K cross E. Now this is what the second, third one. Now let's match with the options. So we have all the things. So k dot is 0, k dot h is also 0, k cross is omega mu h, that we can see from, sorry, this is because b is equal to mu h. So you have to put it back here, mu h. So this is also true. And this fourth one is k cross h equal to minus omega mu f e naught. So that is also true. So you have this. Can This way, we can find out that in case of plane wave angular frequency omega, the proper Vixen vector in the medium Maxwell equation reduces to this following the option. In the fourth option, k dot e is equal to 0, k dot h is equal to 0, k cross e is equal to mu omega h, and the k cross is equal to minus omega. Uh, this is typo here. This would be epsilon. So this would be minus. This is typo. This is the fourth one, but fourth one is correct. This is a typo. I will correct it. Now let's go to the next question. So we have been given a electric field. Question number 9. We have electric field E equal to E naught sine of kx minus omega t plus phi. An electromagnetic fields component in a vacuum. The pointing vector, what will be the pointing vector? So now we have been asked what will be the pointing vector. So we have seen that this k vector is sorry, this uh, k cross p vector is nothing but this omega into mu and omega into mu into h. So, but vacuum mu is equal to mu 0. That means this k cross e vector will be, so this will be this. And now what you can do, you have been given this thing. So you have to just check the cross product of this thing, and we can see that it's this k vector is nothing but kx I cap, because we can see it's propagating in x direction. So we have this kx uh, that is k into kx cap into e cap, and so e naught is given in some direction. So we can, okay, let's not go there, but we know that we can write this. So, okay, so this is this. Now what you can do, we have this h. So we can write it as, uh, we can write this as 1 over mu naught omega mu naught and k upon k cross b. Okay. Now the Poynting vector is given as E cross B over mu, but we know that in vacuum B is equal to mu naught H, so we can write this. So it will be also mu naught because it's in vacuum, so we can modify the equation. So E cross B will be mu naught H upon mu naught, so it will be E times H, and we know that the, sorry, this Poynting vector is like this. So we have 1 over omega 0 E cross k times E. So this is the Poynting vector that we are interested in, and we can calculate this Poynting vector using this equation. Okay, so if we know that in what direction k is going, then if we know the with certainty the E vector in what direction this E naught is pointing, so we can calculate this H vector, and with that we can calculate this E cross H using this equation. Okay, now this is the Poynting vector in the, we also have to know like what are the components of the E, and then we can calculate the H k cross E. Again, after calculating that, we again can calculate the E cross of that vector, and we can get the Poynting vector direction. And we are certain that it will be, it 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 will not be in the direction of E, because it's a cross product with something, something into E. So certainly it will not be E, but we know that it's perpendicular to both magnetic field, electric field, and it's parallel to the propagation direction. So it will be in direction of K. Okay. And the next question is question number 10. So question number 10 is that uh, the space-time dependence of electric field of a linearly polarized light in free space is given by this. So you have a E vector which is polarized in x direction and is given by this cos omega t minus kz. It's propagating along z direction. Then time average density associated with the electric field will be. So we know that the electric field density, energy density is nothing but half of, not half, half of epsilon naught E in the vacuum, it's E square. Okay. And the time average of this, so we have to take the time average. So half epsilon naught comes out, E square goes in, and we have been given that's a polarizing x direction regardless. So you have to write E x cos omega t minus kz, and you have to also write this because the dot product, so the dot here, x cap E naught cos omega t minus kz, and here it is. Now you have 1 by 2 epsilon naught. X dot just becomes, so dot product becomes 1, and then E naught square cos square omega t minus kz. It's a time average. So because it's a time average of this is constant. So it come out 1 by 2 epsilon naught E naught square. And this is a time average of cos square omega t minus kz. And this is the time average. So we have earlier derived this. It's come out to be 1/2. So 1/2 epsilon naught E naught square into 1/2. And this comes out to be UE. This electrical energy density is 1 by 2 into 1 by 2 is 1 by 4 epsilon naught E naught square. So UE part is just this. The electrical energy, the energy stored in the electric component of this electromagnetic wave. It's 1 by 4 epsilon naught E square. Okay, and we can go to the next question. So the next question is uh, a plane polarized electromagnetic wave in a free space is, and time t is equal to 0 is given by this E x bar z 10 j exponential of some e to I 6x plus 8z. Okay, so it's a function of both x and g, but it's the magnitude in the y direction, and it's propagating along x and g direction. So still the propagation is perpendicular to the magnetic field. Now we have to calculate the uh, magnetic field. So we know that first we can write the electric field is given by xg is equal to 10 j of exponential I 6x plus 8z. Okay, so this is this, and we know that B is nothing but in the vacuum 1 over C k cross E, as we have seen earlier. Okay, so let's derive this. So first we have to compare this electric field. Electric field, if we can compare with dxyg is equal to E naught some vector exponential of k dot r minus omega t, but it's t equal to 0, so no need to put this thing is k dot r. So we can compare k, kx I cap, ky j cap plus kz z cap. So we have kx is equal to 6 I cap plus y cap is 0 j cap plus kz 8 z cap. Now we have the k vector. Okay. Now what we need? What we need is the electric field. Electric field, if we compare this electric field E naught with E naught x I cap plus E naught y j cap plus E naught z k cap. So we have this 0 I cap plus 10 j cap. So and 0 k cap. So we have seen that the k vector is only 6 I cap plus 8 j cap, and the E vector is only 10 j cap. Okay, so now when we do this cross product k cross E, it will be 6 I cap plus 8 j cap into 10 j cap. So times this a cross product 10 j cap into this magnitude. This is the magnitude, but the exponential terms are also there. So it will be I, what was there? I 6x plus 8j cap. I 6x plus 8z. Okay. So this is the thing. We can calculate this. So we have this I 6 I cross 6 into 10 is 60. I cross j plus 8 into 10, it's 80. Z cross j exponential of I 6x plus 8j. Now what you can see from here, ijh, I cross jh, you can calculate ij k. So I cross jh k vector 60 k vector plus 80 into j into k into j. So k into j minus I vector. So it will be like minus I of ATI into exponential. You can remove this, and this is exponential of I 6x plus 8j. Now the magnetic field is given by 1 over c k cross E. So we have 1 over c. Here we can copy this and we can paste it here. Paste it here, and this is the answer. So we compare with the answers given. Okay, so we compare with the answers that are given. So we can see that xzt at some time t will be obviously there's this is the light involved. So it's just a spatial component at t is equal to 0. If you impute t is equal to not 0, so t is equal to at t, you can write this as b x y z xz comma t as 1 by c 60k. And minus IAT exponential of 6x plus 8j I multiplied with this. This is the thing. Okay, and the time part. So time part was propagating positive x and g direction. So the minus omega t. So you can write like this: 8j minus omega t, and you can close the bracket here. So this is the 6x plus 8j minus ct, and this is the k direction, only the direction. So that means the magnitude of k will be 6 square plus 8 square, and up this k vector. So the k cap will be 1 by 10 k vector. So that's why this is divided here. So the b vector is divided by 10, 1 over c, 6k minus I 8 exponential of I vector 6x plus 8j minus omega t. This is the baby vector 6k minus I8 exponential of x plus j minus ct. So we can see that the correct answer is okay. Correct answer is C. I think there has been some okay, so this is the C one is the correct answer. Okay. Oh no, we have to also take care of that. This is a velocity into time. So this has dimension of. Okay, this is the correct answer. Okay, C is the correct answer. We can see from here. So omega is nothing but omega into k. K. Okay, so why this is correct? Because k by omega. Uh, sorry, the C. So this is 2 pi by lambda into k by omega is to 2 pi by t. So 1 over this means the omega over k h, this velocity c. So that's why I take k from here. So the omega can be replaced with k into c. Okay. So magnitude of k is 10. K into c this omega, but mod of k is 10. So if this is correct, so then the modified will be 6k minus I8. Sorry, I8, not I8, it's 8i exponential I 6x plus 8z minus 10k. Sorry, 10. K is magnitude is 10. Omega we can replace c and 15. So the correct answer. H, this one, A1. Correct answer is the A1. Okay. Now with this, I would like to acknowledge Professor Manoj Kumar Habibullah from IIT Kanpur NPTEL team. Okay, so with this, I want to acknowledge Professor Manoj Kumar Habibullah from IIT Kanpur NPTEL team, PMR team, and Department of Physics, IIT Kanpur. And I will upload this video on YouTube where you can watch this later on. If you have any doubt, you can ask them in the forum. And the PPT and the solutions will be shared, PPT used in this video and the video link will be shared with you. You can watch it on your convenience. So see you on the next time, next week. Bye.